Good morning, everyone. Again, my name is Christy Buffington, and we have our wonderful instructors here and participants. Thank you so much for joining our day 2 of our Climate and Energy Connections in My Community course. Our theme today is Hot Topics and Energy Efficiency First. A little story to get started. When I was teaching climate change topics, it was really controversial. And many parents were upset that I even was teaching climate change. So I have some perspective of where you're coming from as instructors. Luckily, that was a few years ago. And I think now, not only is it important to teach climate change, but it's also more accepted to teach climate change. So today's theme is to really dive into these hot topics and also to realize that the more efficient that we can use our energy, the less greenhouse gases we emit. You will need today your energy meter. You will need your purple calibration thermometers. And then during the intermission, you'll need some crushed ice, some sort of glass or beaker that you can see through, and some water. And I only have big ice. So what I do is I put them in a Ziploc bag, and I take something and pound it down to make crushed ice, and it only takes about a minute. Also today, you have some information in your modules on Canvas. You can see that there are synchronous climate activities. Those are the things that we're going over in the next hour, 3 hours, sorry. And the presentation that I'll be giving, why the atmosphere is getting hotter and how do we measure it, that's going to be in that is already in Canvas. Elena will be presenting calibrating your thermometer, and then you'll be doing your electric use assignment today. Also, your asynchronous activity tonight is to go through the Cloud Observer and download the Cloud Observer app. You can find all this information today in Canvas. With that, I want to turn it over to Tyler, who will be presenting the first of our 3 energy choice assignments. And you get to choose which assignment you will do and get it done by Thursday and share that in Canvas. And we ask that you read other people's posts about which one they chose and reply to just one or at least one person, one other teacher. All right, go ahead. Thank you.
Thanks, Christy. I'm gonna share my screen real quick just to show you guys where to access the energy or climate choice assignments. If you go to the home page on the Canvas and scroll all the way down to day 3, you will see the energy choice activity down here. Or if you go into the assignments tab within Canvas, it'll be right in the middle of this one block. Makes it a little less difficult to find if you go through assignments. So click on energy choice activity. And there are 3 energy activities or challenges that you can choose from. I'll be going through the solar cooker challenge here real quick. Let's see, probably won't let me pull up this PDF, but y'all have the solar cooker PDF as well as the wind speed challenge and the greenhouse effect in a bottle PDFs on your USB. They can also be found on the Canvas here.
So Tyler, remember we didn't get them on their USBs for this one. I know. We apologize for that. We tried, but we didn't have all 3, so we didn't put them on there to avoid confusion. But they are all here on Canvas.
Yep. So only on Canvas then. And the solar cooker challenge is a really cool one. It can seem a little funny to folks at first because you can go really simple with it and just get some cardboard, some aluminum foil to reflect the light into your closed cardboard system, and a pot to fill with water, or you can put a s'more in there or something to heat up. But you're pretty much creating a small apparatus to concentrate the sun's energy into your own little homemade oven, pretty much. And to show you that this actually works, we have a great example This is a video from Christy, shot a couple years back by her son. I'm going to do a quick share. I might have to reshare my screen because I didn't do the initial audio settings. So bear with me 1 second. Let me get this back online. All right, so real quick, it's pretty, there isn't much talking or audio within, so we may not experience the audio problems that we had yesterday. There will be some music in the beginning, so it'll be our litmus test to see if everyone can hear. All right. So that was Christy's quick example of her solar cooker. As you can see, she has a pretty fancy one. Hers was actually able to get up to 350 degrees, so she was able to bake her famous, is that pumpkin bread or banana bread, Christy?
That one was banana bread, but I usually make zucchini bread or pumpkin bread, something that I grow. And I use it, that was in Montana when I lived there, and I use it in Alaska as well. And I've been cooking solar since 2007.
Nice. That's an awesome example of how you can turn out an actual culinary masterpiece with a solar oven. If you want to keep it simple and just use stuff around the house and you don't feel like going out and tricking out some beautiful solar oven like Christy had, you can simply use some cardboard, some tin foil, heat up some s'mores, do something simple, but make sure you can record some data with it. It would be great if we could get an outdoor and an internal temperature with it. You can use the meat thermometer or the globe thermometer that came in your education kit. So just a little data and some documentation to add to the Canvas is all we're looking for there. And that's all I have on the solar cooker. Christy, which design challenge are we on next?
I think Katie is next.
All right. And Izzy.
And Izzy. Hi, Izzy.
Yeah. So another design challenge that we have is a wind speed challenge. And we had this special opportunity put forward to us by one of a friend project of ours down in Michigan, and at Goddard Space Flight Center from NASA. And they have invited us specially to do a wind speed challenge to help design a way to assess wind speed that wouldn't need a fancy machine anemometer. And we pre-recorded a video because these guys love to talk. They could talk your ear off about wind and kites and whatever. So Christy, would you be able to show the video since you have the audio settings working well on your computer? I sent in the private chat a link. Brett, do you think that you can do a solar cooker and no attack? You think it would get hot enough?
Here.
Sorry, it got muted.
You're muted again, Brett.
Oh, there you go. Okay.
My
Am I good here?
Yes.
Yeah, kind of a funny story. At the end of last year with one of my classes, we tried to build solar ovens and I had an epic fail. I think what was in my solar oven was actually colder than the test one I put outside next to the solar oven. So I think I'm gonna retry the solar oven.
Yeah.
We do get a few warm days, but I bet that it's there are some days that definitely it would not be effective.
Okay. But everywhere, especially no attack, wind speed, you can just devise a way to do wind speed. Christy, were you able to pop it up? Oh, yes. Welcome, Climate and Energy Connections in My Community course participants. We're so excited to have some of our friends here from our NASA Science Activation Network. We have NASA engineer Jeff Bland. He works at Goddard Space Flight Center in Virginia. And we have Andy Henry from Wayne Risa in Michigan. And they run the AeroCats and Rover Education Network, which has youth remotely sensing their environments using rovers and kites alongside globe observations. So thank you guys so much, Jeff and Andy. Give us a little wave.
Thank you, Katie.
We are so excited that
Great
you guys.
To be here.
All right, we're excited to have you extending a special opportunity for us to assess wind speed. So wind speed is important for us in Alaska. We're trying to figure out ways to measure our energy potential in our communities in Alaska. Why do you guys, Andy, what is Aaron, and why do you guys care about wind speed?
Thanks, Katie, and thanks for asking that. So the Aaron Project, in the Aaron Project, we use kites to lift instruments off the ground, and we do things like aerial imaging, where we look down at the ground and try and see how things change over time. And we measure atmospheric variables up in the air and see how it changes from the ground to the air. And in order to do this, we fly kites, and we have to know how fast the wind is blowing, because our kites, we choose our kites based on wind speed. Some fly better in low winds and some fly better in high winds. So it's important for us to know that. For instance, if we don't have enough wind, our kites won't fly at all, and then we can't do what we need to do. But if we have too much wind, we can lose control of the kites. They can crash and break our instruments. They can become dangerous, or the kite line can break and we can lose the kites altogether. They just fly off and take the instruments, and we may never get them again. So, it's actually really important for us to know what's going on with the wind. So that's why wind speed is important to the Aaron Project.
So Globe, they have a protocol to assess wind direction, but they don't have one to measure wind speed. And I was just Googling anemometers, right, on Amazon, and the price was shocking to me. Everywhere from $30 to $300 on Amazon for a device to measure wind speed. And we know that for Globe, which is in over 140 countries around the world, that could be cost prohibitive for a lot of countries. And for a lot of our own families in our country too. So we have a design challenge here, right? That we need to figure out a way that Globe could assess wind speed along with wind direction. Jeff, as an engineer, how do you approach design challenges like this?
Well, first thing you do is define the problem, and I think you outlined it pretty well there, Katie. Measuring wind speed. Classically, there's three separate steps to the engineering phase. First thing is conceptual design. You think of potential ideas, you list them. They can be more than one is better. And then you sit down, maybe have a impartial review person to sit with and kind of explain your approaches. But then you down select and you go to your preliminary design, which means you've pretty much decided on a method or a technology that you're going to use. You may have two, but you've really narrowed the scope. And that's, again, you may introduce some kind of review process with your colleagues to find out, where your problems might be or which one makes sense. Get a second set of eyes on it. Okay. And then thirdly, you go into your detailed design. And the detailed design is when you actually create your building plan, whatever that is, build the thing. After that, go out and test it, but always be prepared when you're testing. Your device is a prototype. It's a prototype. It may not work as intended. So you go back to the start. What's the problem? Conceptual design, preliminary, detail.
That's one of the cool parts of this challenge is they'll be doing exactly what a NASA engineer does. But assessing wind speed, we've been doing this as humans for a long time. Andy, what kind of methods have people been using that we might start to generate some design ideas by using our history and our knowledge from our ancestors to be able to maybe inform our design?
Okay, that's a great question. Indigenous cultures all over the world have always looked at the environment. And everyone has thought about wind on some level at some point. And indigenous cultures have used observations of things in nature to figure out how fast wind was blowing, whether it's blowing fast or slow or very fast. And, things like smoke rising and trees moving and the way that waves move on the surface of the ocean or water bodies. And so we've come to sort of an organic understanding of wind speed by just observing our natural environment. And that's in all cultures, including Western cultures. But in 1805, a man named Sir Francis Beaufort, who was in the British Royal Navy, he developed a scale, and it's called the Beaufort scale. And it still uses those same things. It uses how fast smoke rises and moves, whether tree branches are moving a little or a lot, different things that he sees in, how waves move on the surface of the ocean. The same very things. But what he did that was different was attach a numerical scale to this. And so now we have numbers that represent wind speed, and it's called the Beaufort scale. Well, that's sort of an observational technique. Modern technology and science has been employed to create all sorts of instrumentation that measures wind speed. And a lot of times it's based on, how fast something spins that has blades or cups on it and counting the number of rotations and then turning that into an equation that gives you a speed. But that's not the only way to do it. So we're looking for some novel ideas about how you might design an instrument. And it doesn't have to be that kind of design, or design an observation, something that no one's thought of to measure how fast wind is and then find a way to quantify that.
All right. So the challenge for you educators during this course this week is to try this yourself, and then potentially you'll all have the opportunity to try this again with your students. Any other useful tools? You mentioned rotations per minute, so having a stopwatch might be a useful tool.
Sure.
Maybe a distance traveled if you're using something that floats or moves or pushes in wind. Having a measuring tape or a ruler might be useful. So the goal is use only items that you already have laying around in your house that you think could be repeatable in other countries. These, things that you think that Globe could really use to maybe refine a method to assess wind speed.
That's what you find in nature.
Or that you find in nature, like what, Andy?
I don't know, a tree branch, twigs, feathers, things that the wind moves.
All right. So you guys have your challenge, and thanks so much to the Aaron team and Andy and Jeff for sharing their time to welcome us to this challenge.
Thank you, Katie. Bye now.
See y'all. Thank you.
Good luck.
Dare mighty things, right, Jeff?
Yeah, exactly. Let's do it.
let's do it. So it was really special to have real NASA engineer issue this challenge for our class. And if you don't have a lot of supplies around, this might be the challenge for you. I'm thinking of tenting Terry right now. She doesn't have her school supplies with her. So think about this challenge. How could you measure wind speed using stuff that you already got in your house? This is also a challenge that's easy for kids to do from a distance if you, like us in Fairbanks, are going to be delivering challenges like this for your students. So, and then the last selection for this assignment is designing a greenhouse effect in a bottle. Christy, are you describing that one?
I am. So the last one is more scripted. We're trying to follow some universal design for learning principles in our course that we're teaching. And we also do this with our K through 12 and undergraduate students. And one thing that we like to do, and I'm sure you do as well, is provide some choice for students. And sometimes students need really clear step-by-step instructions. So this third challenge includes step-by-step instructions, if that's the kind of thing that you would prefer to do. And what it is a lesson that's developed by NOAA. NOAA is for the National Oceanic and Atmospheric Administration. And they've provided this activity book. Oops. Okay, so you can see this activity book and here are the table of contents. There's 10 different activities. Several of them can be done for remote learning with your students. And they all follow what's called the climate literacy principles. And these are here on the left in the activity book. What I've provided for you in Canvas is simply this activity, which is titled, I Didn't Do It, Did I? And what it is making your own greenhouse effect in a bottle. It lists what you will need. And in your kits, it sounds like maybe somebody didn't get maybe some tubing in the kit. There's some vinyl tubing in there. There's some modeling clay in there that you can use. And you also have the forestry suppliers, thermometers, those 2 purple calibration thermometers that we'll be using today. You can use this for the activity. It is scripted out and it will look something like this. You've got 2 thermometers with modeling clay holding them in place attached to the bottle top. You have to provide the plastic bottles and you have to provide the vinegar and baking soda that will fizz up and create carbon dioxide, which will then fill one of the bottles, and you can watch what happens with the temperature compared to the control, which is just the regular air that you start with. But the one thing that's so important about this is the math and science connection. We have several math teachers in here as well, and taking time over, every minute. So you'll need a stopwatch and you'll want to record the temperature in the air bottle and in this carbon dioxide bottle and then graph that data. So that is the challenge. And I think you'll find it really fun if that's the one you choose. Are there any questions about these 3 challenges?
And they're due on Wednesday, correct?
They are due on Thursday, and we ask that you put which design challenge you chose, take a picture of it, stick it in Canvas, explain how it went, what worked, what didn't work, how would you do this with students, those kind of things. And then respond to someone else who maybe did the same challenge or maybe did a different challenge. Again, these aren't meant to take a ton of time, but I know me, I've done solar cookers with my students, and we did provide lots of resources. Tyler put those in Canvas, and I got carried away, and I probably spent, days making solar cookers.
Christy, I'm assuming that whatever we do at our house doesn't have to be anything like what we're going to do at school.
Correct.
So I'm going to do the WIN one, but I know I have stuff at school that I don't have here.
Absolutely.
Okay.
We're working with what you got.
For the greenhouse in a bottle, does it matter what size plastic bottle?
No, it doesn't. And you know what? That sounds like a really fun experiment.
Because
Perhaps
I'm thinking
volume
that's
makes a
something
difference.
that we could do online, because most kids would have little water bottles. Okay, thank you.
Yeah, and you could even video yourself doing it and have them video themselves doing it. And wow, I wonder how those graphs might differ with bigger bottles. Students measuring the actual volume sounds like a math connection. Figure out the volume of the cylinder, how much air is in it. Great questions. Okay, so if there's no more questions, we're going to go ahead and launch into a poll. Thank you, Deshanna. I'm always learning more Zoom tricks. Like all of you, I've just started doing this just a few months ago. So wonderful that many of us are integrating local and traditional knowledge. One thing I do want to share is that our Arctic and Earth Science website, which has those videos that you watched for the pre-course assignments, and also yesterday's, if you watched the video from Katie on yesterday's mapping personal observations of change, there's a link on our website with lots of resources about involving local communities and interviewing elders. So I know that some of you are teachers moving from the lower 48 up to Alaska, and you want to know how to be responsive. We have many resources for you to use. Number 2, awesome. Let's share those challenges on Thursday. I can't wait. E-training, globe. Why is the atmosphere? Why is it warmer near the Earth's surface? The surface absorbs sunlight, and then that gets re-radiated out as heat, as infrared radiation. So the correct one is the first one. Number 4, what trace gas is most important in absorbing ultraviolet sunlight up in the stratosphere? So you learned in your E-training yesterday, there are different layers of the atmosphere. The stratosphere is very important for absorbing
kind of a piggy
ozone and keeping it from getting to our surface, because that's what causes skin cancer. So ozone is the correct answer on number 4. Most clouds are found closest to the Earth. The troposphere, tropo means to turn or to mix, and the troposphere is closest to the Earth because that's where we have our weather. That's where the air is moving around and mixing. So that is where the clouds and the aerosol particles are found. Number 6, here's where we're going to be doing some learning today. The 3 most abundant, oh, I spelled abundant wrong. Sorry about that. Typing the poll this morning. Gases in our atmosphere. Number 1 is nitrogen. The second most abundant gas is oxygen. And it looks like we were given trace gases a bigger spot than they actually have in percentage. Did you know that 1% of our atmosphere is argon? So I'll stop sharing these results. And give me a second while I start sharing my presentation, which is hot topics.
Christy, so which one was number 3? You said with the results, you said the 1 and 2.
Sorry, number 3. Oh yeah, I skipped that one. Let's review. Why is the atmosphere warmest near the Earth's surface? I guess I covered it. That's because the surface.
No, I mean the third most abundant gas.
Argon.
Argon. It is argon. Okay, yes.
Argon is 1% of our atmosphere. All those other gases, which water vapor, methane, carbon dioxide, those are all trace gases. Very, very, very tiny percentages, but so important, as we'll see here in a minute. have to declutter my screen here. Okay, so let's start this with a question that you might pose to your students. What if our Earth, instead of being what it is and what we see, is instead this dark body? We call them, in NASA calls them black bodies. And what if it was just this dark body orbiting the sun? Would Earth be colder or would Earth be warmer? I want you to write your prediction in the chat. And if you feel like, oh my gosh, what an easy question, I'll write your prediction in the chat, I challenge you. What would the actual temperature be of the Earth in Celsius? Go.
Good question. Christy, do you see that question is what is the average temperature of the Earth right now?
Yeah, we'll cover that in just a couple slides. I'll not share that yet.
Okay.
But I love it. I love the question. Ooh, we start seeing predictions. Right. So if Earth absorbed all the light from the sun, we would have an approximate average temperature of 5.3 degrees Celsius. Now get your purple calibration thermometers out and try to find 5 degrees Celsius on there. And if you need conversions, use the conversion, put in the chat. What is, yeah, Susan, you're right. We were all way off. What is 5.3 degrees Celsius in Fahrenheit? Anybody jump to it quickly? Put it in the chat. Awesome, thanks, Nicolette. 43 degrees Fahrenheit is what if Earth absorbed all the light from the sun with no atmosphere. So next one is, you know, we can see the Earth from the moon. That means that it's not a black body. If you can see it, it's reflecting light. And so Earth reflects about 30% of its incoming light from the sun. So my next challenge for you is, without an atmosphere, what do you think the temperature of Earth would be with 30% light reflected from the sun? So if it looked like it does now, it just didn't have an atmosphere, what would the temperature be? Go ahead and put your guess in the chat in Celsius. Heike, do you already know all this stuff? That's awesome. Yep, Chastity, it would be cold. So our guesses are around -10. Heike, who's an engineer, mentioned -20 degrees Celsius, and she wins the prize. We would have an approximate average temperature of -18 degrees Celsius. You know what that means? All of the water on the planet would be frozen. But that's not what happened. Luckily, it looks like my clicking's not working here in my sharing. Here we have an atmosphere, and it keeps the Earth's temperature, to answer your other question, around 14 degrees Celsius. So my animations aren't working right now, so I will go ahead and move forward in this, because now that won't work without the animations. So what's really going on is that we have something called the greenhouse effect. We have incoming visible light, solar radiation. If it were just reflecting and had no atmosphere, it would all just return back to space. Although it's about 30% of it would return back to space. But instead we have this structure called the atmosphere that is like layers of glass in a greenhouse. Now, the land, the surface, the water absorbs the visible light and re-radiates that as infrared, which is heat. And that's what happens in the roof of the greenhouse and the walls of the greenhouse. It traps the heat from going out. But you can see the arrow that I drew here. The visible light goes right back out of the roof of the greenhouse, whereas the red, the infrared heat, gets trapped and re-radiated within it, keeping it warm. So we want to understand the greenhouse effect and also provide all of you with resources you can use for your K through 12, and for those of you who teach undergrads, resources you can use in the classroom. We also want to share why we should measure temperatures in our communities. So I have resources from Dr. Paul Stackhouse that he gave me permission to share, and he made this storybook for you and for all the teachers in our Arctic and Earth Science program. He made it into a storyboard that can be printed or that can be shared on the web as an actual storybook. So for those of you who are English language arts teachers, this one's for you from a NASA scientist. We learned yesterday that most of our energy on Earth comes from the sun. And in 1 square meter, that would be about 6 60-watt light bulbs. And that is multiplied for every square meter of the Earth. We can sense that energy in different ways. We see because of visible light. And we feel heat from the campfire. That is called infrared energy, otherwise known as heat. NASA is busy orbiting the Earth with satellites, and those satellites are sensing different types of energy with their instruments. Also, we're studying space, and all of the different types of energy from the sun shining down on Earth maintains this perfect balance or equilibrium that allows us to survive on Earth. The sun is hot. However, space is cold. And one of the misconceptions that came up yesterday is that the sun is just giving off heat. Well, actually, it's the Earth that absorbs the visible light and radiates the heat. The rest of space is just cold but dark space, even if it's fairly close to the sun. So if all of these types of energy from the sun are always shining down, again, that question that we want to explore is, how do we get this perfect balance of energy that allows us to live? We can't live on Mercury. It's hot because it is too close to the sun, and it absorbs that visible light and makes it hot. The average temperature on Mercury is 167 degrees Celsius. We can't live on Mars. It's too cold. It's farther from the sun and has a super tiny, thin atmosphere. And when I used to teach physical science, the students got so excited because Mars doesn't have the same kind of magnetosphere that we have. So the magnetic field of the Earth helps hold in our atmosphere. So Mars is only about 65 degrees Celsius. The third rock from the sun, though, Earth, is perfect for life with an atmosphere. It'd be too cold for life without that atmosphere. So how do we get, and here we have our average surface temperature here of 15 degrees Celsius, and now it's 18 degrees Celsius. And how do we get that way? We get that way by our energy budget. Here's our energy budget described step by step. Energy enters the Earth system from the sun. Some of that gets reflected. You can see here that this cloud is reflecting visible light and energy back to space. But once it gets to the surface, the ground, the trees, everything else, especially the oceans, can absorb the energy. But some of the surface is white and snow. And so that will reflect energy and bounce it off right back out to space. This is what that reflection or albedo looks like. You can see the North Pole here is reflecting Arctic sea ice are bright and reflecting sunlight in May 2001. Whereas here the South Pole is in winter. There's no sunlight to reflect, which is why it's dark in this picture. It's important to know that cold objects emit less energy and warm objects emit more energy. And so that's a feedback. As the Earth heats up, it's already warm, so it's going to heat up more because it's going to emit more energy. So most of that heat gets stopped on the way out. Only a small window shown here in this tiny little orange line is allowed to just escape back to space. Most of it is reflected right back and re-radiated back to the lower atmosphere. And not sure why the shared drive thing shows up in here. My bad on that. Let me fix that. So what I'm going to show you are some demonstrations of things that you can use with your students. And what we have is a demonstration that I want to show you. Here we have the percent of the atmosphere is 78% nitrogen, about 22% oxygen, only 1% argon, and the rest, a tiny sliver in here, are greenhouse gases. And that tiny sliver is really what's causing our greenhouse effect. So I have this picture here of some balls, and I will stop sharing. These are models that you can use with your students. And I got these from Mobile Climate Energy Labs. So nitrogen, you can see that this little model is made of tennis balls. It's a bond here, and nitrogen gas is held together by oxygen, and we have oxygen gas. There's 2 oxygens, little model students can hold. Here we have a little orange tennis ball, argon. And basically, if solar radiation is going to come through the atmosphere, it's going to pass right through these balls, these models, and if they're reflected, it'll pass right through them again. These don't do anything to absorb heat. However, we know that we have some trace gases that are called greenhouse gases. And this model has carbon in the middle and 2 oxygens. Now, some of you chemistry teachers or college professors might say, well, why are they all the same colored ball? We're worried, we're trying to share the concept of the whole molecule rather than the individual elements in the molecule. So we've got carbon dioxide, and what happens when energy hits carbon dioxide is that it starts to wiggle. You can see that nitrogen gas, nothing can make it move. This is a pretty solid bond here, whereas this carbon dioxide gets excited and starts to move. Then what happens if we have more carbon dioxide and one is starting to move and bopping into the other one? Pretty soon now we've got 2 carbon dioxides that are re-radiating and absorbing heat. And then students really can play with this and start showing what happens when you've got more and more carbon dioxide in the atmosphere. And now I want to show a PhET simulation. A show of hands if any of you have ever heard of PhET. Okay, Jennifer, Dacia, Nicolette, Marcy, awesome. Another show of hands if you've used PhET. Okay, Dacia, Jennifer, Nicolette, and I'm sure I'm missing some of you. Nicolette, do you want to share how you've used PhET while I get it up and running, please?
Sure. I haven't used it a ton because I primarily teach APES and environmental science, and I feel like PhET's really good for chemistry and physics. I know they're increasing their models and their simulations that they have now for bio, but I think I used a PhET simulation, I'm trying to remember if it was PhET or Pivot, about like, I think it was actually PhET, and it was in another PD this summer, and it was about increasing radiation to show, wait, let me see. It was about greenhouse gases and how they react and like the movement. So I'm not sure if that's a simulation we're going to do now, but I did one. Okay.
Awesome, thank you for sharing that. So I think you can see my screen. I've got the PhET simulation up right now. These are all free. You just need a teacher account, and then all the lesson plans. Teachers have created lesson plans that you can plug and play, and many of them are digital that you can use in remote learning. So this is the one I used with my students, just demonstrate.
With PhET real quick. Several of this is just my experience. I've used PhET a ton because I teach physics. Several of the PhET labs are still, you need a Java player, and a lot of our students don't have Java players on their computers, or like the ones our district has doesn't have Java players. Greenhouse Effect is one that is a Java player. So they either have to find a Java player or they don't. If you are using PhET a lot, anything that has a flash are ones that almost all students can use no matter what. So they're really good about telling you if it's a Java versus a PhET simulation.
Yeah, thank you for sharing that. I really ran into that a lot also when I used Chromebooks. I had to only use ones that were HTML. And luckily, and I just donated some money to PhET because they have been converting everything since this COVID thing so that they can run just in a browser. So pretty soon, every single simulation will be compatible and you don't need Java anymore, which, you know, my browser doesn't even support Java. So thank you for sharing that, Jen. All right, so here's a little thing that we can do with our students. Remember, this is about temperature and measuring the temperature. And we can add different layers of greenhouse glass instead of gas. And you can see how once you start trapping the red photons here, which is infrared, they get bounced back, but the visible light passes right through. So the more you add, students will soon discover the more the temperature increases. Let's go back to that model that I was sharing. So most of the atmosphere is nitrogen gas. What if I blasted nitrogen gas with visible light? Write in the chat what you think will happen. Okay, I'm hearing people say that nitrogen gas might become excited. Okay, others are saying nothing will happen. Okay, so, and somebody else said they wanted more of these things, so we can build our atmosphere and make more of them. So here we go, we're blasting nitrogen gas, which you can see this triple bond in here, and nothing happens. And this is visible light, okay? What if we blast it with infrared heat? Nothing happens. All right, so we learned that nitrogen gas is not going to absorb heat. How about oxygen, our second most abundant? also not doing anything with heat. How about the visible photons? Visible light, nothing. How about if we try carbon dioxide? Okay, remember what we did here? Write in the chat what you think will happen once we blast carbon dioxide with visible light. What will happen when we blast it with visible light?
Hey, Christy, we got about 4 minutes left before we said we are going to give them a break.
You bet. I'll do it. Just,
okay.
I'm almost there.
All right.
Thank you for the heads up. So what do you think will happen? Okay, a lot of people are saying that it will move faster if we blast carbon dioxide with visible light. Is that true? Is carbon dioxide moving at all? It's not. Remember, visible light in the Earth's energy budget passes right through our atmosphere. It's the Earth's surface that is actually so active in absorbing it and radiating it as heat. So here we have an infrared photon. Now what's happening to carbon dioxide? We are now causing those molecules to jiggle around and re-radiate heat in different directions. So now students can build their own atmosphere. And methane is what is a big problem in Kongiganac. As the permafrost is thawing, more and more methane gets released to the atmosphere. And what does that do with heat? Okay, that accelerates all of this heat being trapped in the atmosphere. So this is a couple models that you can do. One is a physical model. One is a electronic, PhET is an online model. And I've posted in Canvas all of the NGSS standards correlations for using models. And what I also want to show and what I want to close with, so I reshare my screen, is all of the materials that Paul Stackhouse, our scientist, has provided to you as teachers for you to use in your classroom. So in his storybook, he has links to other PhET simulations for you math teachers. He has a equation that you can use for putting in the albedo, the reflectivity of the Earth, and figuring out what the temperature would be. He has energy budget lessons, an entire unit plan, a greenhouse effect video, additional NASA teaching resources, more background resources for your own learning, how to use actual NASA data to have your students explore NASA data and visualize it. And then I wanted to share, lastly, 2 resources outside of NASA. And I will, from current slide, this is called CLEAN, Climate Literacy and Energy and Awareness Network, where Colleen and I actually met. And they have what's called a CLEAN collection. You can teach climate, you can teach energy, and you can search all their hundreds, actually thousands of lesson plans by grade level and standard. And then lastly, climate literacy principles as well through NOAA. So those are some resources that you have available to you. And at this point, we are almost ready for our break. We do have some things that we need to do during the break. And Elena, it looks like I cut into your time a little bit. So Colleen, Elena, how do you think about we allow Elena to go ahead and share what she is going to talk about, and then we start our break a little bit later.
Yeah, we can. I think we just give them still give them 30 minutes. So if we start a little later, they just come back a little later.
Sound good? So you guys stay tight. Elena Sparrow is next up, and she's actually going to show us how to use these purple calibration thermometers to measure temperature and to do it accurately across the whole globe.
Okay, so in making observations, what do we use? How do we make observations? Just a quick put it in the chat. How do we make observations? What do we use? Senses, yes. Is there anything else we can use besides the senses? Our eyes, ears, taste, feel. We use models and we use instruments. Yes, we use tools. So the next question is, how do we make sure that the tools that were given actually works? So and that's the reason why, yes, you all got it, calibration is needed. So to calibrate the thermometers that were given to you, first of all, make sure that the column is not broken. If it is broken, then there's a way for tapping it straight down on the tables so that, or actually, you know, putting hot water so that it all start rising, but check if the column is not broken, and then you can do the calibration. And for calibration, we are going to follow the standardized method that the GLOBE program has been using for calibrating thermometers. And we call this the calibration thermometer because then after we calibrate this, then we use this to calibrate other thermometers, for example, digital thermometers that we may hang in the weather shelter. And so you would need ice and you would need water. And the recommendation is having more ice than water. And I usually use 2 to 1, you know, 2 volumes of ice to 1 volume of water. And then you would put it in a container, whether it's a beaker or a glass or a mason jar. So you can use mason jar, and you would, when you leave it there for 2 to 3 minutes until the temperature of the thermometer is 0. And you know that the thermometer is calibrating well. For this thermometer, it is accurately calibrated when it is within plus or minus 0.5 degree Celsius. So, and when you read it, you don't take it out like this. You have to read it with the thermometer right still in the mixture of ice and water, and then read it through. That's why we need clear glass, so that we can, if need be, we can read it through the glass. And this thermometer is saying it's right on 0. So this is good. Now, if your thermometer does not read 0 or within plus or minus 0.5 of 0, then you'll have to have a new thermometer, because then, you know, that's not going to work properly. And so, the one thing that we were, so after checking for the broken column, then you can do the ice, and have your students check actually, even before looking at the broken column, is also to see what the scale is reading. Can they see the 0.5 hash marks on the calibration thermometer? That's one of the things before using a tool, to have them look, what are the scales, what's how accurate it is. They can't say it is, the temperature is 5.05, because the accuracy of this temperature is only to 0.5 scale. And so I think for the during the break, that's what we're going to ask you to do, is to calibrate your thermometers. And when you know that it's calibrated, then measure the temperature of the room that you are in. And you're asked to put your temperatures on canvas.
Hey, Elena. It
Yes.
sounds like the thermometers they got are Fahrenheit ones, which I didn't realize.
They're Fahrenheit?
Yeah, I don't know if the wrong ones got ordered or what. I didn't look at them before we sent them.
Oh.
So can they do a scale within, if it's 2.5 degree scale, can it be plus or minus 2.5 degrees for the calibration?
Yes.
Okay. Yeah, so whatever the scale is.
Oh my goodness. Right.
And paid for Celsius. So I need to know from everybody if they sent you Fahrenheit, because that means the order was messed up. So
okay.
We need to know. It sounds like they are Fahrenheit. Oh, that's too bad. Okay.
Yep.
So what happened
apologies for that.
Yeah,
yes.
my apologies.
Can you hold yours back up? Sorry, we didn't see it. Or I didn't see it.
It is.
It should look like this. They should be purple. Yeah. Okay, so they're purple. They're just the wrong.
In Celsius.
Okay, so I will contact the company. Thanks,
right.
everybody.
Yeah. So even if you use it for determining temperature, it's okay. We will, then report your temperature in Fahrenheit.
Yeah, Globe luckily you do have to report the temperature in Celsius. However, the good news is that you can use this with your Globe Observer app on your phone, which we're using tomorrow, which is your homework tonight, to get Globe Observer. And in the Clouds app, you get to enter the current temperature, and you can enter it in Celsius or Fahrenheit. And this is a calibrated thermometer, so you're going to be looking at 32 degrees, plus or minus 2 degrees when you calibrate it today. And what it means by calibrating, you're going to make sure that temperature is reading accurately, so you know the thermometer is accurate. You're actually not going to fuss or change with the thermometer at all.
Yes.
Know if it's accurate. And so tell us what it reads at, and then you can still use it for Globe Observer, because the Globe Observer team at NASA will make that conversion for you from Fahrenheit to Celsius. So these aren't all wasted. However, if you actually are using this and one of you emailed us about getting a weather shelter, and if you're using it in a weather shelter, you'll need one in Celsius. And so contact me, because I can order
send
those
you.
and send them to you. Okay, Colleen, would you be willing to share where they put it in Canvas once again, so they have some clear visual directions?
Yes, I can do that. So I was smart and put it in student view ahead of time this time. And so when you are looking at this, of course, we are under day 2 now. I don't know where the time goes, but here we are under day 2. And so here you can click on the calibrating your thermometer. which we have it as a discussion post, not as a graded assignment, although of course we still would like you to submit. And so this is where you submit what the temperature is. So you'll hit reply at the bottom. You'll say what the temperature of your room is, which of course is going to be in Fahrenheit. My little clock thermometer next to my desk is in Celsius and it says 19.9 C, so I'll just put that for there right now, non-calibrated thermometer. And this, and then you also answer the question, why is it important to have standard procedures for data collection? Now, some of you were ahead of the ball, and there are some posting, like 7 of you have already posted, which is fantastic. I forgot to actually say, measure the temperature of the room, and so I edited that this morning, so most of you who replied didn't put that temperature in, which is fine, so just reply to your own post if you've already answered this prompt question, to just reply with the temperature that you have in your own room. And we'll discuss that a little bit once we get back, but for now, record the temperature in your room, answer the prompt question, and you are good to go. And then you'll hit post reply. You can also find this under the discussion side. If you don't go to it from the modules, you'll find it there. Okay. Any questions on that? All right, stop my share then. And so I think we have nothing else. So it's 10:12, or we want to give you a half an hour break. So let's say round that to 10:45 to come back. So you guys we want to make sure we give you a full half an hour break to get some more coffee or tea and do your measurements and calibration. And we will see you back at 10:45. And yep, Nicolette, just make do with the best that you can about your package. Can you mute the computer, Jane? Yes. That you have to go down to where the mute button is and hit the little arrow next to it. And you can say leave computer audio. And so then you won't hear us. You'll still be able to see us while you're listening to other things. And then you will be able to leave computer audio, and then you can join back to the computer audio at that same location.
Oh, wait, could you say that again? I've never not been the teacher. So how do you do that?
Yes, so down on the left, yeah, I had to figure this out when I had 2 going yesterday. I had my tablet. I had to do that before. My tablet on one, my computer on the other. So on my Mac, it's on the bottom left. If you hover over the bottom of the screen, and you have your mute button, and there's a little arrow. There's a little arrow to the right of it. And then you can say leave computer audio. So then you won't hear it. So that was nice when you have 2 going. Like I said, I had my tablet yesterday. Yeah. So then you can just mute us. You don't have to listen to us. I'm not sure I should be sharing that with you, but there you go. But no, I totally understand. You've got to multitask, got other things going on. You can mute us, still have us going, then you don't waste the time.
Okay. Welcome back, everybody, from the break. And I just wanted to touch on what the GLOBE program is about, which most of you have already learned, but just wanted to make sure that everybody does have this. So in the GLOBE program, there's many different areas of investigations. On this picture on the left side, you can see in the orange colored, the different investigations: atmosphere, biosphere, hydrosphere, and pedosphere. And so we're focusing more on the atmosphere in this course. And over 100 million environmental measurements. Actually, it's now over 150 million environmental measurements are archived in the GLOBE program. That's available for use for our students and for anybody, including undergraduate students and even scientists. And I've actually had publications based on GLOBE student data. And so the GLOBE program is a experiential, the minds-on, hands-on program. And so, and operating in more than 100 countries. I think we're 123 countries now. Okay, and the next slide is about the, and the GLOBE program is very necessary. It's good for student studies, but also in providing ground-based observations to validate the remotely sensed data that is being gathered by the many satellites of NASA. And this slide shows the A train, which is short for the afternoon train, but there are many satellites, the Aqua, CloudSat, Calypso, Parasol, Aura. They all are behind one another on the same track, on the same orbit, and they complement and they collect complementary information, and some duplicate measurements from a different type of sensor. So we just wanted you to know that the student investigations, student observations are really important, because GLOBE is one of the ground-based observation campaigns. Okay, and so now I think you have all, here's the training materials and the protocols, and the including the current air temperature protocol link. Okay, Colleen.
All right, thank you. Any questions? Oh, I guess I do want to say one thing, and maybe Elena, you want to go over this. I think we can spend a few minutes on it, of the importance of how you use this activity when you're in a group setting, when everybody's in one place, because I think that's interesting.
Oh yes. So what we've done, if they're all, we're all together, one activity that we have done is use different thermometers, from the body thermometer that's being used, or the thermometers that we use outside our homes to determine what the weather is telling us for the day, for what the temperature is for the day, and different types, including a calibration thermometer that we will resend the correct calibration thermometer. But anyway, so the activity is to try and get your students to measure the temperature of the room that they're in, that we're all together in, and then share the temperature. And then the question is, can we make sense of the data that we're using from using these different thermometers? And so so the question is, how can we make sense? Is there do we need the same do we need to use the same thermometer for comparison? And how about specific instructions or methods for actually determining the temperature? And so in the GLOBE program, we have weather shelters for putting it outside our school, or in our yard, or in an experimental plot to determine, or a automated weather station like that some schools like Joy has. And so it's just trying to get the students to think about, the importance of the need for standardized protocols. So I see somebody saying that it's 78 degrees in their living room, and somebody says it's 62, and in the tent it's 58 degrees Fahrenheit. And then Joy, Hamilton, and Shagaluk it's 15 degrees. And so, you know, to try and make sense of all this temperatures, you know, what do we need to be able to compare it? And usually it's eliciting responses from the students. And then, yeah, which we're kind of trying to simulate here in the chat. Yeah. So so it's important to try and because that could be a source of inquiry for students to start out with. How do I measure the temperature in the room? And or if you're outside, do you measure it in the shade? Do you measure it in the sun? Do you measure it close to the pavement or, you know, close to a tree? You know, they will find out that they will get different temperatures by doing that. And so it's good to, and even in the one of the assignments on the greenhouse effect, think about what are the things to make it so that you can have comparable data where you have the control and where you have the carbon dioxide being produced in another bottle. So.
Thank you, Elena. I think that was great. Everyone's having a lot of fun with the temperature differences. That's a nice thing, right? We talked about this activity ahead of time. We're like, well, normally we do this, everyone's in their room, but it adds another dimension to it, right? Everyone's in a very different location, climate, you know, whether you're inside or outside, like Terry.
I just want a quick ask for all the elementary teachers who have joined. When I taught middle school, I had an 8th grader, super bright student, aced all the tests, knew the textbook right front to back, and had not used a thermometer ever in his life until my lab. And so I had the thermometers, they were glass, they were in plastic tubes, and he took the plastic tube with the thermometer in it and stuck it in the beaker and had no idea that that wasn't how you measure temperature. And it dawned on me that the student had never held this device anywhere in an elementary school. So I just beg you to please have students start collecting observations and doing measurements in the younger grades as well, to build those schools for the middle and high school grades.
And these thermometers, the thermometers that we gave you, they can also be used for measuring water temperature. And that's why you would put a string to it so that they can have a hold, or even put it over their wrist so that they don't lose the thermometer in the water.
Okay, are we good? I'm just getting my PowerPoint ready. All right, cool. There's a lot of energy connections there, which is good since that is our next topic. And, you know, when I introduced myself earlier, one of the things I failed to do was mention how I had actually taken a globe training from Elena and Katie right after I finished my student teaching. So back in 2012, I went up to Fairbanks and did a globe training with them, which my mentor teacher was a globe teacher, and she introduced me to it. And so it was great to, when I started at this job in the last couple of years, Katie and Elena and I have been kind of crossing paths a couple of times. And one of the reasons why we were really excited to be able to do this collaboration is there are a lot of energy and climate connections. There's a lot of overlap and really great things that can be included and interwoven in both of our works that are related, and which is why we're so excited to teach this class and share some of those connections. I mean, we don't have enough time to even talk about everything that we would want to talk about, but hopefully giving you an idea of where to start and where you can start finding some other resources, or you find topics that are particularly of interest to you, and you know how to at least start including some of these in your classroom, and hopefully increasing your own knowledge about these different pieces, like with Christy's poll this morning about the top 3 gases in the atmosphere. as a not random example for increasing your own knowledge. So some of the connections between that, we started talking about measuring the temperature in your room, and the heating is a big piece of our energy use in Alaska, which I'll be covering in this presentation. And so it's a pretty good connection there. Now, I'm going to be kind of starting from the basics here and working my way up to some more complicated topics and energy use that we have in Alaska. Today, I'll be focusing on energy efficiency and conservation. And tomorrow, when we have an energy piece of the class, Tyler is going to be talking more on the renewable side of it. So I'm happy to answer questions about renewable stuff, but if you do have questions on that, let's try to keep that on this. I'll have the chat up here and try not to be too distracted by comments that are coming in from the chat, but hopefully one of you can stop me if there's a question that you would like me that I should be answering, because I do want to answer them as we go along as much as possible. And I will try to stay within my time here. I'm going to try to do it in about 45 minutes. So we'll see if I can do it. So the first one here, I wanted to remind you of this energy literacy that Tyler had shared yesterday, which was this definition from Department of Energy. And so I'm wanting to today increase some of your own energy literacy. If you've taken a class from me or Tyler before, or read, then you have seen some of these slides before, but I'm really trying to also weave it and make the connections back to some of the other things we've been learning about climate and globe. Here are those 7 energy literacy principles. The whole packet that describes and defines each of these energy literacy principles is also on your USB drive, or is on the Department of Energy website. But I want to point out that it starts out really basic, like energy is a physical quantity that follows precise natural laws, and goes all the way up to quality of life of individuals and societies is affected by energy choices, which is, of course, is a very strong climate connection. And so another climate energy connection here is, I'm wondering if you guys can think about this before you answer this question. I want you to think about it so you're not all putting it at the same time. And what are the top 5 ways to reduce our global carbon footprint? And I want you to see if you can identify 2 of them. So put 2 of your guesses in the chat. What do you think they are? And it actually doesn't, I say climate energy connection, but I'll give you a hint, they're not actually all energy. So you can think about some other things that maybe are not energy as well. Cool, I'm seeing some good ones come in. All right, yeah, not just all about energy, good. A lot about energy, okay. Camp more often, Tent and Terry, love it. Not using all that energy to heat our homes. Just get a sleeping bag. More yoga, I'm a fan. Okay, so these are based on this research. Well, it's based on a bunch of research from thousands of different researchers, but condensed down by one specific editor and a team of scientists that worked with him. And they identified the top 80 ways that we are going to reduce. Now, I didn't quite emphasize this, but this is important. This is looking at it globally, right? So globally, how are we reducing our carbon footprint? And we'll get a lot more local for like Alaska or your community scale. And so the number 1 is onshore wind. So reducing carbon, the biggest way to do that is transition our fossil fuels, and some of that should be transitioned to wind. Health and education, right? We're all educators here. So education is a big piece of that. Understanding your choices, whether they have to do with energy or not, or carbon or not, but just in general, improving health, and then the education as well. Plant-rich diets, I saw a lot about eating local and eating less meat. I definitely started reducing. Now, keep in mind, this is not saying be a vegan, right? This is plant-rich, not plant-only diets. But definitely affected my choices to start eating even less meat than I was before. Refrigerant management, which was a surprising one. And the initial one, this was actually number 1. When you think about those refrigerants, those chlorofluorocarbons that are in there, they're actually 10 to 100 times more potent than CH4, than methane or carbon dioxide for trapping those greenhouse gases. And so even if there's only small amounts of it, but we have been making some progress with that. So it has started to, I think, lower down, even though it's still one of the top 5. And then number 5 is the tropical forest restoration. So reforesting and helping support that huge carbon sink of tropical forests, which have been decimated in recent years and continue to be decimated. So those are the top 5 ways. And so this is, we're talking about climate. We all shared some really important, impactful ways that climate has affected us and the communities that we live in. And so I really try to think about, here are some of solutions, right? So people are already researching. These are all solutions that are available and scalable. That was an important part of their research, is these were things that could be applied today and could be scaled up to a way that we could use it. Not theoretical things, not things that couldn't be scaled, that could only be used locally, right? These are things that can be used in a large area. And so that's why it's a global one, not necessarily locally. Locally, your solutions might be different, might include some of these, or it might not, but these are global solutions. And this one, they have 2 different scenarios. And so this is for 2 degrees, if it ends at 2 degrees carbon of warming, and the other one was 1.5. I went with 2 because I'm pessimistic that we'll actually get to we'll be able to stop at 1.5. Might be too late for that. I'm a little pessimistic maybe on that, but you can look at both of those options. The website is drawdown.org if you want to look at and they have information about each of these. You can dig into this more. They also have an educational, thank you, Dacia, because I'm not sure how to pronounce it. And so this is, good question, Laura. I don't know why tropical forests in particular and not deciduous. My guess would be is that because deciduous are losing their leaves part of the year, and not growing part of the year, tropical forests are growing and absorbing that carbon year round, would be my guess.
Can I make a guess? This is Nicolette here. So I don't know that this is accurate, but we teach about a lot of tropical forests are basically torn down for agriculture, especially in the Amazon. And with that, when the land is torn down, like destroyed for agriculture, it stores much less carbon. And then it ends up being like basically it gets decimated within a few years because of slash and burn agriculture. And so even after it has been like torn down, it is much less productive, I think, than really a deciduous forest area.
Yep. I think probably both of those are contributing factors. I mean, food, energy, water. We talk about the food, energy, water nexus a lot in Alaska. Maybe not as much in lower 48, may not hear as much. We definitely talk about it, especially the energy. Food is very important worldwide, and thinking about where we get our food from, how we're getting it, how it's being produced, and the energy that goes into that. If you think about your different trophic levels, I had that pyramid that you have, like the amount of energy that is actually absorbed from like the cows eating the grass, how much energy they absorb from the grass, and then the people eat cows or the wheat, right? And so it's much more efficient for us to just eat that wheat or whatever vegetable much more directly, instead of that energy, just the straight energy loss in terms of number of calories, but also the amount of energy of like electricity and heating and water and everything that goes into those. All right, I know I'm not going to hit my 45-minute mark here if I keep going on this. So I just get so excited about it. I'll keep moving. Can dig into that more. Love the conversation and the insights here. So go to the next slide. There we go. There's also climate literacy principles, which were developed by similar people from the energy literacy principles. Getting the thumbs up from Christy. So I just wanted to share, I like sharing these right after the energy literacy principles as well, because there have a lot of overlap, obviously. You know, as you can see, the sun is the primary source of energy for Earth's climate system, right? Which was shared in Dr. Stackhouse's storybook. And this is also very similar to the #1 energy literacy principle. And then going on down to the consequences for the Earth system and human lives, which again is similar, but you know, different, but similar and related to our energy literacy principles. And then there's some research too, you know, why do we work with youth on energy? Why REAP's, a lot of REAP's focus, and of course, almost all of my focus is on working with youth or training teachers who work with youth around energy awareness. And so their values, just like any other values, are developed when they are young. And then there was a study that was done in California where they sent students home with energy efficient light bulbs, and teachers, parents at home signed off saying, yes, we changed out some of our light bulbs for these energy efficient ones. And then they took this survey, and 71% of those parents said that their children influenced their purchase or behavior on energy efficiency. And as you know, especially in the smaller Alaskan communities, the schools, that's the center of the community. And that can be really impactful, not just on the students, but then sharing on with their families as well. So this is another prompt for you to put in the chat. What is energy? And thanks for sharing that, En-ROADS. I'm not as familiar with that, so I will have to look at that myself. But I would like you guys to answer, what do you know? What do you think, if you know the scientific definition, or if you don't, what do you think energy is? I'd like to see you put that in the chat. Mamie, who's taken like 3 classes from me, is on top of it. Okay. Great. Yep. Ability to do work is the definition, but you guys are also, these kind of the other things that you guys are putting in there are different ways of saying the same thing, right? You can do work to have some sort of power to make things move, right? Or have a chemical reaction or generate heat. All of those are within that definition of the ability to do work. And so what are our 2 main types of energy? You know what those are? Yeah. Matter transformation, Brooke. So what are our 2 main types of energy? Yep. Potential and kinetic. Yep. So there are our main types, kinetic and potential, the different ones within that. So a lot of different things are going to be associated with those, but those are kind of talk about the kinetic with the motion energy, or the potential or stored energy. Okay, so kind of wanted to give some basics so we're all on the same page there with talking about energy, and hopefully starting that basics of energy literacy for you, or reminding you. I had to be reminded of this when I first started at REAP, some of that information, so I thought that you guys wouldn't mind me sharing some of that as well. And I'm going to dive a little bit more into Alaskans' energy use, how we use energy. There's going to be a lot of graphs on here, so stick with me and feel free to throw in questions if you have them. And I'll talk a bit about efficiency and conservation as well. So kind of starting with the importance of this, right? With less than 5% of the world population, the US consumes about 18% of its energy. So per capita, we are using way more energy, and that's looking at electricity, heating, transportation, all that energy. We're using way more than many other people in the world. Of course, that's also associated with producing way more carbon emissions per capita than most countries in the world. So thinking about this is why we talk about efficiency, right? It's not just a matter of transitioning all to renewables, but we also need to be thinking about being more efficient with what energy we are using, whether it's renewables or non-renewables. And so we talk about this in terms of efficiency and conservation. They are technically 2 different things. Conservation is your behavior change. So we're talking about what the temperature in our room is. So if we're kind of cold, like some people were saying that they prefer 62 degrees, and I'm like, I am freezing, my hands are cold. It's like 63 in my house right now. I refuse to turn on the heat. My hands are cold. I'm not going to do it. But I put on this sweater instead of turning on or turning up the heat. And so that is a behavior that I chose so that I'm not using that natural gas, which is how my house is heated. Now, the efficiency part of it, which I also do, is having a programmable thermostat. And so this is something where you set the temperature. So when I do have my heat on, I have the temperature set to lower. Of course, before I started working from home in March, I had it set to lower during the day when I wasn't at home. And just kind of be high in my comfort range, which is in that 68 to 70 range is my most comfortable range inside. And I only have that temperature for like an hour or 2 in the morning and a few hours at night when I'm actually at home and just sitting, right? And not actually doing a whole lot of activity before I go to bed. So those are like an example of using technology like a thermostat. And technology doesn't have to be something that's computer based, right, or fancy. Technology is just, it could also be better insulation, right? Using some nicer insulation. And then the conservation is your behavior change. So there's a lot of different ways that we can do this to reduce our energy use. And so we talk about energy efficiency, and a lot of people tend to, and sometimes I fall into this trap too, is efficiency. We talk about it in terms of efficiency and conservation, right? Our behavior and our technology. So, just as a caveat there, but we do talk about it as the first fuel. So less energy we use, right? That's less fuel that we have to use. That's the first fuel that we think about. It's always cheaper than new energy generation. So this graph is a little bit old. It's from 2014, but it does show, and this hasn't changed, that energy efficiency is always cheaper. So if you think back to the Kong video when he was talking about capturing that waste heat, for example. So instead of, it's still going to be cheaper than putting in more wind turbines to produce electricity, which then can be transferred to heat. Instead, you just capture the waste heat from their existing power plant. And that's going to save, it's going to be cheaper to do that usually than putting in something new. Now, wind generation in the lower 48 is the cheapest form of energy right now in the lower 48 other than efficiency. So this 2014 bar, where it shows, and this is levelized cost, so cents per kilowatt hour. So if all things being equal, how much does it cost per kilowatt hour to install this or build this? So this has actually come down even more. In Alaska, that tends to be hydro, which is not on this graph, is where our cheapest amount of electricity is other than efficiency. Okay, so another piece of this is the buildings, right? And so buildings are a big use of energy. And this is a commercial building graph, but schools also fall under the commercial buildings when they are looking at this from ASHRAE. So operations is 50% of the lifetime cost for a building, which is, I just bought a house in January. So looking at this 14% financing, the cost of it that I have to pay over the lifetime of owning this house, be a little bit discouraging, but that's okay. I also know that operations are 50%. This is a pretty energy efficient house. I can make a lot of choices that can reduce its energy use. And so that cost, those operations are a big piece where you can save money and of course, reduce your greenhouse gas emissions by being more efficient in the operations of your buildings. There's a lot of benefits. I mentioned, of course, the just straight utility cost savings, right? Like less paying for electricity or however you do your heating, less maintenance usually, increased value. There could be tax benefits depending on where you are. Mitigating risk, okay? Public relations, I mean, let's be real here. This could be something when people say they get a LEED certification. They blast that out to the world. Look how efficient we are. This is great. Like, that can be a good thing too. And then an interesting point too is like higher morale, which then can also impact your productivity. So when I'm in the office, like Tyler, who's relatively new to REAP, he's just finding out how inefficient our office buildings are, a little bit embarrassingly, where we rent for our REAP offices in Anchorage. And it is freezing in the winter and sweltering in the summer. And so that is not the most efficient way for us to be working, as when we're too hot or too cold. And so that can make a big difference. And in the previous graph, I had said that the lifetime cost for a building, this actually doesn't include your personnel. So the costs for the salaries of people, they don't usually include that. Sometimes they do, depending on what sort of analysis that you're doing, but this doesn't include like the salaries of the maintenance workers and the teachers or whoever, right, whoever is working in that building, office workers working in that building. And so this can also create potential savings. So there's a lot of benefits to efficient buildings. Even other than just your reduced carbon emissions. And this is how we talk about it a lot at REAP. Christy mentioned earlier how sometimes we run into that resistance of talking about climate change. And sometimes we still run into that as well. We don't lead with, this is why we're doing it, right? We lead with, here are some of the benefits that you can find from this. It's not just about, and some people that is really important for them, but for everybody, saving money is important. So it's a good way that we talk about leading with it. Now, another connection in rural Alaska is a community called Quinnahock, which is in Western Alaska. And the Cold Climate Housing Research Center, or CCHRC, you see their logo in the top left of that photo. They partnered with the members of this community to build this house that is super energy efficient, but all that also follows traditional housing principles. So they worked with elders and others who lived there to say, well, what kind of house has worked and, has worked historically before colonization, okay, before westernization of communities, what sort of principles worked well. And a design they came up with was octagonal, so 8-sided, and this helps shed the wind. There are other pieces to it, like an open floor plan. The square footage is similar to housing, and it's multifamily. So there's pieces to it that they worked with the community. But in addition to that, it also saved on heating. So the average house uses 800 gallons of heating oil per year approximately. And this prototype uses 180 gallons of heating oil per year. And this was the first one that they built, and they built several after that. I also want to make the comment here too, I have like the adaptation to climate. And they had an issue with the foundation because of the permafrost changing. And so they had to redo the permafrost after the first, I can't remember if they had to redo it for the first one or they redid it for all the next ones. I do know they had to change the foundation because of that. But this is also, looking at your unpredictable weather, this is, like I said, very efficient, and so saving your money on this as well. And does anybody who, with a raise of hands or a thumbs up, those of you in Alaska, who participate in the energy rebate program? Anybody here do that? Some people, yeah, okay. Maybe some of you. All right. So the energy rebate program, back when they had it, I'm sorry, go back. There we go. They had, I know, solar incentive. Well, federal solar incentive we got at least. So you have that home energy rebate program. The weatherization program is kind of still around, but not funded nearly as much. But there was an average savings of 30% per home. So you got a rating of your home. You did a bunch of the recommendations that they provided with that rating. And then you got another rating, and then you got some money back from it. Of course, they don't have that energy rebate program anymore, but that was something, 30% per home. Yeah, okay, thank you, Thelma, for sharing that. I also, for that link to the CCHRC prototype information. This slideshow is also in Canvas. I uploaded the PowerPoint slides, and I linked to the Google Slides presentation, and I include as much as possible links to everything that I am sharing so that you can find out more, go back and find out as much as you can. And usually in the notes, because I don't want to clutter up my actual slide with a bunch of links that you can't click right now anyway, but they are in the notes of this. So you can go keep digging through it. So when you're thinking about this, a house, okay, you have fuel that's coming in like from a power plant for your electricity, and that's about 35% efficient. Depending on it, could be up to 50% efficient if you have a very efficient natural gas power plant. We have a couple of those in the Anchorage area. But still, you're not getting a huge amount of efficiency there. Solar panels are around like 20% efficient. I think they keep getting better, but still not great. And then, so you have that efficiency, and then you lose a lot, right? Then you don't have as much efficiency going out. Same thing with fuel, heat 80, that some of the really efficient boilers are like 95% efficient, around there. Nothing's 100% efficient. And then you have that energy loss, a lot of times in heat, right? Even it's going to be lost in the form of heat. You can't keep everything in perfectly. And so the better that you can keep that heat in, the better you can use your lighting. We talked about passive solar briefly yesterday, I think. So maximizing that use of your light that you do have, all of that is energy efficiency, and thinking about that in terms of the house as a system. But then also not forgetting about things like ventilation. You can't just seal up your house and make everything keep all the energy in and then also trap toxic gases that end up being in there or get moldy houses or whatever. So there's all these different pieces that go along with it. Can't just be easy, got to be complicated. All right, so now I'm going to share a bunch of graphs about energy, how we're using it in Alaska. Again, everything is linked, so if you want to dig into these or how I got these, all of them are linked in the notes of the slides, which you can view. All right, so this is from the Renewable Energy Atlas, which you guys have physical copies of from your kit, as well as ability to download it. It's on your USB drive, and you can download it online for free from REAP's website. So here you can see, I mentioned that because this can probably be a little bit hard to tell on this PowerPoint presentation, really small, but you can see there are different types of ways that we get our electricity generation. And this is really dependent on what we have available locally. So up towards the Fairbanks area, you can see that there's a lot of coal because you have the Usabelli coal mine nearby. In South Central, there's a lot of natural gas because we get natural gas from Cook Inlet and use that for electricity and our heating, though the heating isn't included on here. In Southeast, you see a lot of hydro, right? There's a lot of rain down in Southeast Alaska. So you can see now, of course, that's not exactly everything, right? We're not getting, but that is, you can see generally where all of this is coming from. And then in other areas where they may not have access to natural gas, especially for electricity or hydro, you see these oil droplets. So they're importing diesel fuel or fuel oil. They're generally used interchangeably, those terms, to generate electricity in their communities, along with some wind along the coast, which Tyler will talk more about yesterday. Oops, double slides there. There we go. As does the cost, right? So cost is not the same across for everybody. In the lower 48, now I have a pretty good idea of what you guys pay for electricity in lower 48, but I'm wondering if you guys know what your electricity costs are. Can you type it in the chat? What do you, if you don't mind, per kilowatt hour? You paying down there. Yep, 9 to 12 is usually what I see, 9 to 12 cents per kilowatt hour. Okay, Nicolette, you might pay extra for wind if you have that opportunity, pay a few more cents per kilowatt hour for wind. Yep, and so here, our cheapest is around Juneau. Kodiak has a similar cost for electricity, 14 cents, but you can see it's much higher even in Anchorage. Matsu pays about the same as Anchorage does, 19, 20 cents per kilowatt hour. Okay. Great question, Jane. I'm glad you asked. Do you remember how Juneau gets its electricity? What's down in Southeast? Hydro. Yep, they got a bunch of hydro. They've had hydro plants in Juneau for over 100 years. So they've already paid for that huge investment cost of those dams. And so they're able to keep their electricity prices low because right now they don't have to build new ones. Eventually they will, right? Or produce electricity from other sources as it continues to grow. But that's how it is. Now, Barrow or Utqiagvik, they get their electricity from, what's up in Barrow? You guys know what Barrow is? Or Utqiagvik? Not wind. What industry is up there? The North Slope. They have oil, and what do they get? What can't they send down the pipeline that they also get a lot of with oil? What comes up with oil?
Natural gas.
Natural gas, yep. So they get a bunch of natural gas and they don't have a natural gas pipeline. So they basically are, I think they get it for free or for very, very cheap electricity for that natural gas. They're able to produce their electricity with Utqiagvik and other nearby communities. They use that natural gas. And that's one of the reasons why people talk about a natural gas pipeline, like down to Fairbanks, right? They pay 20 cents, 22 cents per kilowatt hour there from coal. Natural gas is more efficient and could be potentially cheaper, but there are huge environmental costs associated with that and an additional pipeline. So not something we're going to get into today, but just an example of how complicated that energy conversation can be. So the other thing I want to point out, I think my next slide talks about power cost equalization. So I wasn't familiar with this, also called PCE. until I started at REAP. Embarrassingly, didn't understand about energy in other parts of the state. And so you can see that there's two different prices for some of these communities. You have a lower price and then a much higher price. And so that lower price is what residents pay up to 500 kilowatt hours per month on their bill, or community buildings. Now, schools do not qualify for this. So they and other businesses pay the higher rate for that cost per kilowatt hour. And then anytime a household goes over 500 kilowatt hours, that 501, that rate, that 501 plus anything, those kilowatt hours are charged at a higher rate. So this power cost equalization, this is a quote from the Alaska Energy Authority, who manages this program. And they do it to kind of have the rate similar to what the average cost of power is Anchorage, Fairbanks, and Juneau. So Anchorage's rates have gone up recently in years, several cents per kilowatt hour in the last several years. You see Juneau's down pretty low. So it's kind of some average. They try to get it down close to that rate because there was a lot of investment in that infrastructure of those communities that are on the rail belt or in the capital of Juneau. And so great connection there, Christy. Thank you with Kong. So if you want to dig into this graphic was made by somebody at HFC when she worked there, that kind of talks about how that PCE works, which getting a little short on time, talking too much. So I'm going to keep moving on here. Hopefully you can dig into this and learn more. Yes, PCE is specific to Alaska. So this is something that's only in Alaska for this. There are other types of subsidies, I believe, that happen in the lower 48, but I'm not familiar with them. And of course, the oil industry itself generally gets subsidies anyway. Okay, so for our electricity, most of our electricity is coming from natural gas and hydro. So this, and of course that electricity, most of that electricity is being, if you think about our largest population centers, which are in Anchorage, Mat-Su, Kenai, those are all getting their electricity production from natural gas. And like I mentioned, up on the North Slope, they are using natural gas as well. And then hydro is the next largest. So that's like the Juneau. There is Bradley Lake on the Kenai Peninsula, which provides electricity for everybody on the road system as well. And other hydro projects around the state like Kodiak and Hydrokinetic like Igiugig, which again, Tyler will talk more about tomorrow. And then the rest is that oil, also any type of like the diesel fuel communities, coal, like the Fairbanks area for their electricity production, a little bit of wind, a little bit of biomass, and solar, not producing enough yet to show up on this pie graph, but that is growing. Yep. So Brooke, let's answer your question, I think. And it is really that low, less than 1%, even less than biomass. The biomass that's coming from, I think a big piece of that is from the methane landfill in Anchorage is mostly where that about 1% of biomass is coming from. Mm-hmm. Yep, so solar's still pretty low, but growing greatly in Alaska. And if you talk about, if we switch to rural versus Anchorage, right? This is really important to think about the source of it. Natural gas is far more efficient and cleaner burning than in diesel, which is primarily used in rural communities. Heating is the biggest cost for Alaskans as well. You can see that 69 to 77%, depending on where you live, is going to be the cost for the heating, right? And that's an important piece. It's not just about our air quality, which is very important, our greenhouse gas emissions, which are also important, but that cost, especially when you start thinking about those who carry that energy burden of having to pay for that energy. Again, another rural, just kind of focused on rural energy, that heating piece can be so big, not just by region, which was the previous one, but looking at really rural communities. And the price, again, hitting on this, hopefully you're getting a theme here, right? It's the people who can afford it the least have to pay the most for their energy. You think about your electricity, it's 50, and rural Alaskans pay more than 50% of their take-home pay on energy. That's a really big, important energy burn. You think about that percentage of your take-home pay, what you have to pay towards those bills. There was also a study done by NAACP on income spent on energy, and you can see they're looking at 8%, which is way lower, way lower than what our rural Alaskans are looking at, but still very, very difficult for them to pay for. If you think about the household income around 19,000, pay 8% of your money towards energy bills compared to those who are in the $150,000, then that's looking at, that's a very big difference at 2% versus 8%. And there are, again, I have links to these reports from NAACP. Another important fact is looking at 6 million people who live within 3 miles of a power plant. 39% of them are people of color, which is higher than what the number, I think we're at 34 or 35% of our population are people of color. And so looking at this in terms of who is affected by those coal plants is also really important. Okay, I also wanted to point out who is using this energy, all right? It's not, the residential is about 8%. So those of us who live here are only using about 8% of that energy. And so it's the industry that's doing it, which is mostly oil industry, some mining industry as well, maybe a little bit of our tourism, of course, not so much this year, but they're the ones who are using the biggest part of this energy pie. Transportation is also an important piece to look at because, but this is a little bit misleading, this transportation piece, because Anchorage, depending on the year, is like the 4th or 5th largest cargo airport in the world. And so a lot of this transportation fuel gets put in there, even though it's cargo airplanes coming in and out. I mean, it's still being used here, right? But it is a little bit misleading for what that energy use is. So this is a very busy graph, but stay with me here. But it's interesting, at least I think so, and you could be an energy nerd along with me here. So looking on the left side of the graph, we're looking at our energy usage. Okay, so like at the top, solar, someone's asking what's our solar, 0.03%. All right, this is our source of the energy, no nuclear. And then you can see the rest of the sources of energy that we use for electrical generation, as well as heating and transportation. So you can see those pieces there, the numbers, and of course the size of the bars and the blocks relate to proportionally the amount that's being used, megawatt hours. So on the right then, we have our uses. So like I said, electricity generation, then that's split into residential, commercial, industrial. And then we have our transportation. Now heating is much harder to track. So I said heating earlier, but I don't believe that actually is included on here. This is electricity and transportation. And of course, some of that electricity might end up being used for heating if some people are using electrical heating, but generally this is electricity. So transportation, now on the very far right, these gray boxes, we have our energy services, and then rejected energy. What do you guys think that rejected energy is? Or for people who took the class, see if they remember what we said before. All right, yeah, waste. Yeah, waste mostly in the form of heat. Oh, sorry, was there a question? Okay, yeah, so that's wasted energy, mostly in the form of heat. Especially if you look at that transportation piece, right, which we're mostly using petroleum for our transportation, that piece is mostly lost in heat from those internal combustion engines, industrial, and so that is that efficiency piece. When we talk about the first fuel, if the way someone explained this to me that I thought was really profound, hopefully I can share it, is if we had half of that rejected energy or that wasted energy, and that was moved to energy services, that would be like doubling the amount of fuel that we had available to us. We could actually use that fuel more efficiently. So that's an important piece I want to share there. So this one is Alaska 2018. I also have, and then the state officials estimate that it's $1 billion every year. That's the number associated with this rejected energy. So that's real dollars, $1 billion bonfire that's not being used efficiently. So here's the US as a whole. So you see similarly, huge amount of inefficiencies in that transportation and industrial but a lot more inefficient in their electrical generation, or a bit more efficient in electrical generation. Yeah, so question, I briefly mentioned the methane collection from the landfills. Actually, it's only one landfill in Alaska that is using that, which is Anchorage. And so that would still be considered heat loss, right? Because even burning that, there's still heat that's lost from that, as would be part of that energy efficiency. So if I go back, come on. All right, so you see for electrical generation, looks like they don't have it for some reason on here, biomass. I don't see it going up towards electrical generation. So maybe they consider that as part of commercial, biomass commercial, but that would be. Okay, and then for those of you not in Alaska, this Lawrence Livermore National Laboratory has it broken down for each state, so you can look up your state as well. So I want to mention beneficial electrification. And so this is transitioning your fossil fuel dependent technologies to using electricity. So like your cars transitioning to an electric car, or using an air source heat pump instead of a boiler to be able to produce your electricity. And so it tends to be more efficient. Using it more efficiently, remember that efficiency from vehicles is still, even though our electricity efficiency is not great, it's still more efficient than an internal combustion engine. So it tends to be more efficient even if you're getting it from a non-renewable source. And then if you do get it from a renewable source, then it transitions it to carbon free. So that's beneficial electrification, thinking of these fossil fuel dependent technologies, transitioning them electricity, and hopefully that electricity is being transition towards renewables or already is transitioned. Like in Juneau, where they have all hydro, there's a bunch of electric vehicles there, and they're also getting more air source heat pumps. And so they're taking advantage of that, taking fossil fuels straight out of their community. So some big takeaways I want to share here with you. Our energy, because that was a lot of graphs and a lot of talking. So I'm going to try to summarize my big points here. Our energy production and use is mostly coming from fossil fuels. Whether you're in Alaska or not, this is still mostly coming from fossil fuels. Heating is the biggest use and expense for most Alaskans, and this is disproportionately affecting low income and Alaskan Native communities, low income households and Alaskan Native communities. Not everyone pays the same amount for energy. And although I didn't exactly talk about this, I think this is an important connection, is that not everyone is affected the same by the changes in climate or by the uses of those energy. And of course, efficiency first. So even though I made a really big point of showing one of our biggest ways of transitioning and reducing our carbon is using onshore wind or nearshore wind, even though that's the biggest way to reduce our carbon, it's not necessarily going to be the cheapest. And to maximize that, we still have to be efficient first. So kind of keep that in mind. The cheapest fuel is the one that you aren't using, no matter what the kind of fuel is, whether it's renewables or non-renewables. I'm gonna keep kind of skim past this here. There are, right, I talked a lot about, hopefully not getting too down about like, oh, it's the oil industry using all of this energy. Like there's not, hopefully you don't feel disenfranchised or disempowered by this. There's a lot of great energy and climate solutions that are going on, including the Arctic and Earth Science, which you have some great partners here that are co-instructing with me on this. So great work that's being done out there. There are some resources. I'll again skim past this because you'll have access to this, but some great resources. I also want to highlight CLEAN, which Christy mentioned earlier, where we met. And they also have, there's a couple discussion questions after the climate videos about how do we talk about this in class when you might be having difficulty. And so they have some really good resources on their website for how to bring this up in class, how to talk about climate in class in a really good way. So in my 2 minutes here, I can do it. They might do it in 5, all right? But I still want to leave some time for wrap up at the end before our break. So this is one of the resources, AK Energy Smart, which we've mentioned before. It's a free curriculum developed by REAP before I worked at REAP, and for Alaska Housing Finance Corporation with also CCHRC. And they're all free lessons. You have them on your thumb drive, access to your website, and REAP also continues to update them and add new lessons as we go. So if you have issues with it, it's Tyler's fault and tell him. Oh wait, okay, I guess not. You can tell me, we can figure it out. So how do we measure electrical energy? I'm gonna do a quick excerpt from one of the lessons. We use kilowatt hours, right? Well, what does that kilowatt hour stand for? K is kilo, that's 1,000. This is a great metric connection for students who usually do this with like 6th, 7th graders. Remind them about that metric connection. K is kilo. The watt, this is our unit for power. So this is the rate that the energy is being used. So like you think about miles per hour, right? Our watt is that rate that the energy is being used. And then the hour, this is not kilowatts per hour, but this is hours over time. There's a common misconception, I think, about kilowatt per hour, but it's not. Kilowatt hours over time. So you think about like 1,000-watt microwave, that would be 1 kilowatt. If I used it for 1 hour, that would be 1 kilowatt hour. If I used it for 2 hours, that would be 2 kilowatt hours, or 2 of them at the same time, right? So it keeps adding up over time like that. Then you see, we also go through how much do you think it would cost to use a 60-watt light bulb. Since I'm short on time, I'm not going to make you guys guess. If we're using it for 10 hours a day for 30 days, I'm in Matsu. My current rate is 19 cents per kilowatt hour. And so that would be $3.42 a month, which doesn't seem that bad, except it's only 1 light bulb. So I have this out of order. Here's an example of a bill, and it shows you how much energy you used this month, which here, total usage is 202. Oh, my things are off. I'll have to fix that later. But you can take that 202 multiplied by your rate, 18 cents per kilowatt hour, to get how much your bill is plus your flat fee. All right, so Arctic Star, those of you in Anchorage or have been to Anchorage in the winter, you might have seen this. We're gonna see how much it cost to power it last year. I'm gonna race through this, but again, it's all available online. Anchorage is about 18 or 19 cents per kilowatt hour, plus its flat fee. So Doc, hopefully Tyler will address that because it has to do with the transmission and utilizing. So if we do the math here on how much it cost, this Arctic Star that goes on for 113 days during the winter, it's $9,000 because they still use incandescent bulbs. I kid you not. They are using 75-watt incandescent bulbs. They're not using LEDs. This is a real example. What is happening in Anchorage every winter. So if we use 10-watt LEDs instead, so I show the students this is a theoretical, right? 10-watt LEDs, do the same math. The Fort Richardson, the base, is the one who pays for this and maintains it. It's our tax dollars at work. It would only cost $1,200. So that is a savings of almost $8,000 that they could be having every year that they do not. It's been going on. I mean, they have had some version of it since the 50s. Good question. So I usually have a slide on that. I skipped it this time, but since you asked, I looked up how much it would cost to buy 350 LED bulbs or 375 LED bulbs. It's a couple $1,000s, which is a lot of money, but way less than the amount of savings that you would have over the winter. And they also last a lot longer than the incandescent bulbs. Yep, it would be a couple $1,000s, and you'd probably get some sort of discount. I bet the military can pay way less than what you can at Costco, but I looked it up, like Costco outdoor LED bulb. So then I also go through an example of Lime Village, which they pay 99 cents. Oh, and I have that wrong. It's actually with PCE. Their electric rate is insane. It's the highest one I could find. But for emphasis here, even with PCE, even with some help from the state, it's 99 cents per kilowatt hour. And that'd be $404 a year just for using PS4 and TV. Yep. So the activity that you are going to be charged with is measuring 5 appliances. So you have that electricity monitor that you got in your kit. If you didn't get a kit, then you can look up the watts. And there is, and I'm going to stop my share here so that I can share the Excel sheet. Oops, wrong one. Too many things open. There we go. Okay, so you will download this from Canvas or get it from your thumb drive or the ACA Energy Smart website. And you're gonna put in your electricity rate. I have some rates, these are 2019 rates of some communities, or you can look up, obviously not everybody's community is on here, especially I only have Alaskan ones on here. So put in your electricity rate. If you don't have PCE, these two cells are gonna be the same number, right? So if you don't have PCE, you're in Boston, 9 cents per kilowatt hour, 12 cents per kilowatt hour, it's just going both there. If you have a different rate, this first one is the lower cost with PCE, and the second one is the higher cost without PCE. So you put in those numbers and then you fill out your devices. And I tried to make very clear instructions in the Excel sheet here, but I still want to try to quickly show you. Put in, you can overwrite this computer or change it to what your actual one is, and try to do 5 devices. So try to do at least 5 is what we're asking for. If you want to do more, you can, but we'd like to see 5. You put in the description, the watts, the number of hours, and the number of days. So you fill out these 4 columns here, and then it will auto calculate that cost for you and tell you what your rate, what your total kilowatt hours and your rate is there. All right, and then you will fill that out. We also want you to make that connection with the heat. So take some temperature readings. Use that calibrated thermometer next to your appliances. Like, my computer is warm, right? I'm putting my cold hands on my computer. It's nice and warm for doing all of this work. So put that thermometer next to it, see if it's doing, or if you have like a little electric space heater, see what that is. Measure that temperature. Record at least one of them to put in. There isn't a spot on this sheet because it's not normally part of the lesson, but I'd like you to put it in somewhere here, type it as a note somewhere so we can see it. What was the temperature of one of those appliances that you measured? All right. And then you're going to share that on Excel. Yes.
Holly had a question that I looked at on Canvas. There is no submit button under the student view for that assignment. Okay. So we'll have to throw one in there.
We will fix that. All right. So I only have one more. Whew, all right. I'm only 6 minutes over. Look at me go. I gotta do my, oh, is it not? Yeah. Are you seeing my desktop right now? Okay. So day 2, asynchronous assignments. These are the things that we want you to complete this afternoon if you have not already done them. So the calibrate thermometer activity, if you didn't do that this morning, measure, calibrate it, post whatever your room or tent temperature is, and answer that prompt question. Do this electric use spreadsheet, which I just showed you. Download the Cloud Observer app and complete the wizard, the Cloud Observer wizard is what that's supposed to say, not the wizard. And then send a cloud observation to Globe via the app with the satellite match. So those are the things that we're asking you to do this afternoon. One thing I did forget to do, which I have set up here, is I'm going to quickly show you the electricity monitor. It's pretty self-explanatory, but if you haven't used it before, I'm still going to show you pretty quick what this looks like. So I have mine plugged into my laptop right now. All right, you guys see that? Backwards, but you can see it at least. All right, so we have this. I had just the plugged in. I unplugged it for a while, so it's charging right now. So you can see this is the rate of it charging. And when you plug it in, you don't have to do anything. It automatically turns on. So it automatically turns on. You plug whatever you want to check into it, and it is already on watts. So remember, that's the number that you want for your spreadsheet, is the number of watts. So plug that in. There's other settings you can play with. I'm kind of running short on time here, so I'm not going to talk about it too much right now. We want to dig into it. You can also, look at your kilowatt. If you left it plugged in for a while, it'll calculate some of the kilowatt hours for you. So this has been plugged in for that, but you really want the watts. And if you get off of watts, you just have to hit that button that says watt, and then it'll go back to watts. It's pretty straightforward there. So you want to make sure you're using the watts. It has the W. That's the number that you want for your spreadsheet. Okay, question about the Cloud Observer app. All right. Any questions about this monitor? And again, if you don't have this, you can just look up, I think there's a link in there for some that will take you to where some resources are to look up the wattage. But if not, then you can use your internet to find out, well, okay, how many watts does this make and model normally use? Or use the volts and amps on it. I mean, you can find it if you don't have one of these meters, but most of you should have this. Okay, other questions? All right, so I'm gonna turn it over to Christy to do a quick wrap up.
You bet. So I do want to make one quick climate and energy connection. We talked about these temperature thermometers, and I know that you got Fahrenheit. I'm so sorry about that. So and some of you have some that aren't working. Great. Anyways, if you have one that's not working, send me an email. I will get you one in Celsius that hopefully works. And I'll need your shipping address where you will actually receive it. So you'll have to send me that information. I also need a phone number because we need that when we send stuff out. Secondly, a really fun extension that links measuring temperatures to energy efficiency is that when things are inefficient, when our appliances are inefficient and use a lot of kilowatt hours, they tend to give off heat. So one thing we can do, and I know I start my seeds on the top of a freezer. Why do I do that? Because it's giving off heat. It's an inefficient appliance. Your students can actually measure not only the kilowatt hours, but the changes in temperature from energy use. So I challenge you to play with the thermometers that you do have and put them next to your laptop. You can feel that it's warm. What's the actual temperature? Can you measure it? Put it next to your hair dryer when it's plugged in and not running compared to when it is running. Students can actually measure the changes in temperature and the kilowatt hours at the same time. So that would be a fun inquiry activity and also really link these two concepts together. As a closing today, we do something called the circle, square, triangle, or triangle, circle, square reflection or exit ticket. So I'm going to try to share one that I have hopefully open with you. Okay, bear with me here. What I need you all to do is take out a piece of paper. And on your piece of paper, I want you to draw a circle. I want you to draw a triangle. And I want you to draw a square. This is something that your students can do asynchronously as well. I'll show you an example as soon as I close all these screens. There we go. Got it. Okay, here's an example from my students last fall. This student drew a square, a triangle, and a circle. Doesn't matter what order you ask them to do. And this one has a little bit better handwriting. Next to the square, the student wrote squares with what you already know. Next to the triangle, the student wrote main points I learned. And then next to the circle, the student wrote still circling in my head. So as your exit ticket today, your reflection, I'd like you to write down what squares with what you already know, something you heard today that relates to something you already know. I'd like you to pick one main point of something that you learned and then something circling in your head that you want to learn more about. I'd like you to take a photo of this and share it with us in any way that you can, whether it's in the chat or you can do a teacher message in Canvas or send one of us an email. That would really help us answer what's circling in people's heads and then know what you are gating from this session today.
And Christy, there was a question for me to show the assignments that we need to do. So I'm going to pull that up again while people are working on this.
Can I ask a question about the square, triangle, circle?
You bet.
Since that's so similar to a KWL, would you have them do anything ahead of time, or would you have them do everything after the lesson?
That's a great question. I typically use these, and I know Elena's used them, and Katie, for quite a while, we use them after the lesson, but we actually start with a T-chart or a KWL at the start of the lesson. Often, instead of what do you know, what do you wonder, and what did you learn, this is the learn part of the KWL. And so rather than saying what did you learn, they insert this part, but it also links back to what they said, what did you know in the beginning.
That's cool.
We also use, you know, different words instead of no. We often use what do you you know, what squares with your thinking, and you can use that at the beginning and structure it that way. And then what do you wonder?
Yeah, the idea really is to place your new learning into your already constructed learning. It's a reflection, not to set it up at the beginning. I would probably do the KWL at the beginning and then follow up with this.
Yeah.
Go for it, Colleen.
I had to find my unmute button when I'm sharing. It's a different spot. I was just putting this back up because at least one teacher asked, oh, what were those again? And I think this is a decent summary. If this is what we're asking you to do today outside of this session. That follows with what we have talked about today. So this is also all on Canvas, right? All of these are within the day 2 module, but just another way to see it and remind you of what we're asking you to do today.
Could I possibly ask a question?
Sure.
Looking at the cloud observer, so going through the app in the wizard and the satellite map or match, are the next satellite comes through our area after 11, which I hate to admit is well past my bedtime. And then the one after that doesn't come in until the wee hours of the morn, and then the next one is as we start class tomorrow. So how close to a satellite match do we need to be for this assignment?
I believe it says in the Wizard app that it's within an hour is what they ask. So if you want to do it like within the hour before our class starts, that would be fine as well.
So I think the times are a little confusing. Sometimes in the satellite, you have to, when you load Globe Observer and you set your local time, you have a choice, I think, to have it be on universal time or local time. And so that always confused me when I first started using it. My guess is that those times may or may not be like in the middle of the night. Most of them are in the afternoon. So most of the satellite matches, when I get notifications, are the A train. They're the ones in the afternoon. And I can just ignore all the other ones that are coming up. Globe also, if you can't get out to do a satellite match, Globe is really happy with solar noon observations when the sun is at the highest point in the sky. And there are local solar noon calculators on something called mynasadata.gov. And they're also on the Globe Observer. They're buried in that website for Globe Observer of when your local solar noon is with your location settings turned on. That way there's, you know, that protocol with a common way of measuring and a common time of measuring to use around solar noon. And then Susan just said, there's a spot the station. So you can actually find what station is near you at any time as well, if you go to spotthestation.com.
Okay, I have to go. So I'm gonna stop my share and get going. There was a question, if we're done for the day, we are. That we were just kind of staying on to answer questions. We are done. As Christy said, please share anything with us, your circle, triangle, square, and in any way that works for you. And I'm going to head out. These guys are probably going to stay on for a little bit longer, but for the rest of you, I will see you tomorrow.
Thank you so much, Colleen. And I'll stop recording, but I'll still go ahead and stay.